Listening practice. Forward earthquakes are among nature's most formidable challenges, striking without warning and leaving devastation in their wake. From the ruins of ancient civilizations to modern megacities, seismic events have reshaped landscapes, economies, and human lives. The 2011 Tohoku earthquake in Japan, the 2010 Chile earthquake, and the catastrophic 2023 Kahramanmaraş earthquakes in Turkey underscore a sobering truth: seismic resilience is not a luxury, it is a necessity. This book emerges at a critical juncture, where climate change, urbanization, and aging infrastructure amplify the risks posed by seismic hazards. Earthquake-resistant structures, design, analysis, and innovations bridges the gap between academic theory and real-world application, offering insights gleaned from decades of research and hard-won lessons from disasters. It challenges engineers, architects, and policymakers to rethink conventional practices, advocating for designs that prioritize human safety, adaptability, and sustainability. The journey from seismic vulnerability to resilience demands collaboration. By uniting cutting-edge technologies like AI-driven risk modeling and self-healing materials with time-tested principles of ductility and energy dissipation, this book charts a path toward structures that not only survive earthquakes but also inspire confidence in communities. Let this work serve as both a tribute to past failures and a blueprint for a safer, more resilient future. Preface. Scope and objectives. Earthquake-resistant structures, design, analysis, and innovations is a comprehensive guide to understanding and mitigating seismic risks. This book spans foundational seismology, advanced structural dynamics, and emerging technologies, equipping readers with the tools to design, analyze, and retrofit structures in high-risk regions. Key objectives include: 1. Education, demystify seismic design codes, ASCE 7, Eurocode 8, and performance-based engineering principles. 2. Innovation, explore breakthroughs like base isolation, shape memory alloys, and 3D printed components. 3. Practical application, provide actionable retrofitting strategies, compliance checklists, and global case studies. 4. Policy advocacy, highlight frameworks for enforcing seismic safety in informal settlements and historic preservation. Target audience, engineers and architects, master ductile detailing, base isolation, and retrofitting techniques. Researchers, delve into AI-driven seismic simulations and bio-inspired design. Policymakers, leverage case studies from Japan, New Zealand, and Turkey to shape resilient building codes. Students, gain a holistic understanding of seismic hazards through theory, formulas, and real-world examples. Structure and unique features. Part I establishes the fundamentals of seismology and structural dynamics. Part 2 dissects seismic design principles for concrete, steel, and masonry. Part 3 showcases innovations like self-centering systems and AI monitoring. Part 4 grounds theory in practice with global case studies and community resilience strategies. Appendices offer quick reference tools, design formulas, retrofitting plans, and compliance checklists. This book is not merely a technical manual, it is a call to action. By blending science, ethics, and creativity, we can transform seismic resilience from an engineering challenge into a shared societal commitment. Let me know if you'd like to refine specific sections further. Part I, Fundamentals of Earthquake Engineering. Chapter 1, Introduction to Seismic Hazards. 1.1 Seismology Basics, Plate Tectonics and Fault Mechanisms. Key Concepts. Plate tectonics. The Earth's lithosphere is divided into tectonic plates that move due to mantle convection. Boundary types. Divergent, plates move apart, e.g., Mid-Atlantic Ridge. Convergent, plates collide, e.g., Himalayas. Transform, plates slide past each other, e.g., San Andreas Fault. Fault types: normal, tensional stress, reverse/thrust, compressional stress, strike-slip, shear stress. Earthquake mechanics: focus/hypocenter, the origin point of seismic energy underground. Epicenter, the surface projection of the focus. Seismic waves, P waves, fast, compressional, S waves, slow, shear, surface waves, most destructive, e.g., Rayleigh and Love waves. Magnitude versus intensity, magnitude, logarithmic scale, Richter, moment magnitude, measuring energy release. Intensity, qualitative scale, modified Mercalli, describing local effects. Example, the 1906 San Francisco earthquake, M7.8, occurred on the San Andreas Fault, a transform boundary, causing widespread fire damage due to ruptured gas lines. 1.2 Ground motion characteristics, PGA, spectral acceleration and duration critical parameters, peak ground acceleration, PGA, maximum acceleration, measured in g, 1 gram equals 9.8 m/s superscript 2. Directly impacts inertial forces on structures, e.g., 1994 Northridge earthquake, PGA 1 gram. Spectral acceleration, SA, frequency-dependent amplification of ground motion, plotted in response spectra. Engineers use SA to design for building resonance, e.g., short versus tall structures. Duration, prolonged shaking increases cumulative damage, e.g., 2011 Doku earthquake, 3-6 minutes of shaking. Influencing factors, soil type, soft soils amplify shaking, e.g., 1985 Mexico City earthquake. Directivity, directional focusing of energy near faults. Design implications, building codes, e.g., ASCE 7, use SA to define seismic forces. PGA guides base isolation systems in high-risk zones. 1.3 Seismic risk assessment, probabilistic versus deterministic approaches methodologies, probabilistic seismic hazard analysis, PSHA, evaluates all potential earthquakes over a time frame, e.g., 10% probability of exceedance in 50 years, used in modern building codes, e.g., U.S. National Earthquake Hazards Reduction Program. Deterministic approach, focuses on a maximum considered earthquake, MCE, scenario, e.g., worst-case fault rupture, applied to critical infrastructure. Nuclear plants, dams. Risk versus hazard, hazard, natural phenomenon, ground shaking. Risk, combines hazard, vulnerability, structural weakness, and exposure, people/assets at risk. Case study, Los Angeles, uses PSHA to zone high-risk areas, enforcing stricter building codes. Japan's tsunami barriers, designed deterministically for Doku-scale events post-2011. Key takeaways, earthquakes arise from tectonic interactions, with ground motion parameters, PGA, SA, duration, dictating structural demands. Risk assessment blends science and policy to mitigate societal impacts. Next steps, Chapter 2 will explore structural dynamics to quantify how buildings respond to these seismic forces. This chapter establishes the scientific and practical foundation for designing earthquake-resistant structures, linking geophysical processes to engineering solutions. Chapter 2, Structural Dynamics and Earthquake Loads. This chapter introduces the mathematical framework for analyzing how structures respond to seismic forces, progressing from simplified models to complex systems and practical design tools. 2.1 Single degree of freedom, SDOF, Systems Key Concepts, Equation of Motion, \m\u, t, plus c\u, t, plus q, t, equals m\u_g, t, \m\mass, c damping coefficient, k stiffness, u, t, relative displacement, \u_g, t, ground acceleration, natural frequency and damping, natural frequency, \omega_n equals \sqrt frac km damping ratio, backslash zeta equals backslash frac C2m backslash omega underscore n backslash, dynamic response, free vibration, solution decays exponentially based on damping, backslash zeta 1 backslash underdamped, backslash zeta equals 1 backslash critically damped. Forced vibration, solved via Duhamel's integral or Newmark backslash beta backslash, method for seismic input. Design insight, SDOF models approximate simple structures, e.g., water towers, and form the basis for modal analysis in MDOF systems. 2.2 Multi-degree of freedom, MDOF, systems key concepts, matrix formulation, /m // .u /+ c // .u /+ k /u equals m /iota .u underscore g, t, / m / c / k mass, damping, and stiffness matrices. /iota / influence vector distributing ground motion. Modal analysis, 1 solve eigenvalue problem, /k /phi equals omega 2m /phi /. 2 decouple equations using mode shapes /phi underscore I /. 3 superpose modal responses, SRSS or CQC for closely spaced modes. Example, a 10-story building modeled with 10 DOF, 1 per floor, captures interstory drift and torsional effects. Design insight, higher modes, e.g., second, third, significantly affect tall buildings, necessitating multimodal analysis. 2.3 Response spectrum analysis and design spectra key concepts. Response spectrum, plot of maximum response, e.g., /s underscore a / s underscore v / s underscore d / versus natural period, /t underscore n / for a given damping, /zeta /. Design spectrum, smoothed, code-based version, e.g., ASCE 7, Eurocode 8. Incorporates inelastic behavior via ductility reduction factors. Steps for analysis, 1 compute natural periods, /t underscore n / and mode shapes. 2 for each mode, obtain spectral acceleration /s underscore a, t underscore n, /zeta, /. 3 combine modal responses, e.g., SRSS, /r underscore / text total equals /sqrt sum r underscore I2 /. Example, a bridge with /t underscore n equals 1.2 /sec and /zeta equals 5 %, uses /s underscore a equals 0.5 g / from the design spectrum. Design insight, tripartite plots unify /s underscore a /s underscore v and /s underscore d for broad frequency range visualization. Elastic versus inelastic, design spectra often scale elastic demands by ductility, e.g., r equals 8 for ductile frames. Summary table concept SDOF MDOF response spectrum complexity single mass, 1 DOF multiple masses, coupled DOF simplified design tool analysis method direct integration modal superposition code-based spectral values key output application time history response modal participation factors peak acceleration / displacement. Simple structures buildings, bridges seismic design codes discussion questions 1. How does damping ratio, /zeta / influence the width of the response spectrum peaks? 2. Why is the CQC method preferred over SRSS for structures with closely spaced modes? 3. How do building codes address soil structure interaction in design spectra? Conclusion. This chapter equips engineers with tools to model seismic responses, from basic SDOF principles to advanced MDOF and code-compliant design spectra, ensuring structures withstand earthquakes through informed dynamic analysis. Chapter 3, Performance-Based Earthquake Engineering. This chapter focuses on designing structures to meet predefined performance goals under seismic loads, emphasizing safety, functionality, and resilience. Below is a structured breakdown of the key concepts. 3.1 Performance Objectives, Immediate Occupancy to Collapse Prevention. Definition: Performance objectives define the desired structural behavior under specific earthquake intensities. These are categorized into 4 levels: 1. Operational, minimal damage, critical facilities, e.g., hospitals, remain functional. 2. Immediate occupancy, minor damage, safe for reoccupancy without repairs. 3. Life safety, significant but reparable damage, ensures occupant survival. 4. Collapse prevention, severe damage, prevents total collapse but requires demolition. Standards: FEMA P58, quantifies performance via probabilistic loss assessments. ASCE 41, defines acceptance criteria for seismic rehabilitation. Example: a school designed for immediate occupancy post-earthquake ensures no structural damage to classrooms, while a warehouse may target collapse prevention to prioritize cost efficiency. 3.2 Ductility and energy dissipation concepts. Key terms: ductility ratio, \mu \mu equals \frac delta underscore u delta underscore y delta underscore u ultimate deformation before failure, delta underscore y yielding deformation. Hysteretic damping, energy dissipation through inelastic material behavior, e.g., steel bending. Design strategies: ductile detailing, reinforced concrete, confinement ties in beam column joints. Steel, reduced beam sections, RBS, to concentrate plasticity. Energy dissipation devices, viscous dampers, e.g., San Francisco's Salesforce Tower. Buckling restrained braces, BRBs, in the LA City Hall retrofit. Case study: the 1995 Kobe earthquake highlighted the importance of ductility. Buildings with poor detailing collapsed, while ductile structures survived. 3.3 Fragility curves and risk mitigation. Fragility curves, definition: probability of exceeding a damage state, e.g., cracking, collapse, versus seismic intensity, e.g., PGA. Development: empirical, historical damage data, e.g., 2010 Chile earthquake. Analytical, nonlinear time history analysis of structural models. Risk mitigation strategies: 1. Retrofitting, adding shear walls or base isolators to reduce fragility. Example: Istanbul's historic mosques retrofitted with FRP wraps. 2. Code updates, post-2011 Tohoku earthquake, Japan revised codes to address tsunami loads. 3. Public policy, incentives for seismic upgrades, e.g., California's SB 1953 for hospitals. Example: fragility curves for a mid-rise apartment might show a 40% probability of moderate damage at PGA equals 0.3 grams, guiding retrofit priorities. Integration of concepts. Concept role in PBEE performance objectives define target outcomes, e.g., life safety. Ductility ensures controlled deformation to meet objectives. Fragility curves quantify risk to prioritize retrofitting and policy. Discussion questions. 1. How does ductility enhance a structure's ability to meet life safety objectives? 2. Why might a hospital prioritize operational performance over collapse prevention? 3. How do fragility curves address uncertainties in seismic risk modeling? Conclusion: performance-based earthquake engineering integrates objectives, material behavior, and risk analysis to create resilient structures. By balancing ductility, energy dissipation, and probabilistic assessments, engineers safeguard lives and infrastructure against seismic threats. Part 2, Seismic Design Principles. Chapter 4, Design Codes and Standards. This chapter outlines the backbone of seismic design, codes, load combinations, and risk prioritization. It bridges theoretical principles with practical compliance for engineers and policymakers. 4.1 International Codes, ASCE 7, Eurocode 8, and IS 1893 1. ASCE 7, United States, Scope, applies to buildings and non-building structures. Key features, defines seismic design categories, SDCAF, based on risk. Uses risk-targeted maximum considered earthquake, MCER, ground motions. Case study, California's * Hospital Seismic Safety Act mandates ASCE 7 compliance for critical facilities. 2 Eurocode 8, Europe, Scope, covers buildings, bridges, and industrial structures. Key features, dual design philosophy, no collapse and damage limitation under 475 and 95-year return periods. Soil classification, AE, amplifies spectral acceleration. Case study, Italy's 2016 Norcia earthquake validated Eurocode 8's ductility requirements for masonry retrofits. 3 IS 1893, India, Scope, addresses high seismic zones, Zone 2V. Key features, zone factor, /Z/, ranges from 0.10, Zone 2, to 0.36, Zone V. Response reduction factor, /R/, accounts for ductility, e.g., /R equals 5 for moment frames. Case study, Budge, 2001, earthquake prompted stricter IS 1893 revisions for Gujarat's reconstruction. Comparison table, Code Seismic Zones Ductility Factor Soil Considerations ASCE 7 SDCAF /R equals 38 Site Classes AF Eurocode 8 PGA Based Maps Behavior Factor Q Soil Types AE is 1893 Zones 2V R equals 35 Rock, Medium, Soft Soils 4.2 Load Combinations and Seismic Force Calculations 1. Load Combinations, ASCE 7 /1.2 D plus 1.0 E plus 0.5 L plus 0.2 S /D dead load, E seismic, L live load, S snow load. 2 Seismic force methods, equivalent lateral force, ELF /V equals C _ S /W C _ S seismic coefficient, S _ DS /R /I _ E W effective seismic weight. Response spectrum analysis, modal superposition for irregular or tall structures. Example, a 10-story office building in Los Angeles, SDCD, /S _ DS equals 1.0 G R equals 8 I _ E equals 1.25 C _ S equals 1.0 /8 1.25 equals 0.156 W equals 15,000 text K and V equals 0.156 15,000 equals 2,340 text K and 3 Eurocode 8 approach, F _ B equals S _ D, T, /M lambda S _ D, T, design spectrum ordinate, lambda correction factor, equals 0.85 backslash 4T2 backslash T underscore C backslash dash 4.3 Importance factors and occupancy categories. 1. Importance factor, backslash, I underscore E backslash, adjusts seismic forces based on structure's societal role, backslash, I underscore E equals 1.5 backslash hospitals, fire stations, risk category 4. Backslash, I underscore E equals 1.25 backslash schools, assembly halls, risk category 3. Backslash, I underscore E equals 1.0 backslash residential slash commercial, risk category 2. 2 Occupancy categories, ASCE 7, I, low hazard, agricultural buildings. 2. Typical occupancy, offices, apartments. 3. High occupancy, schools, theaters. 4. Essential facilities, hospitals, emergency centers. Case study, Japan's tsunami evacuation buildings, assigned backslash, I underscore E equals 1.5 backslash, to ensure post-earthquake functionality. 3 Eurocode 8S Importance classes, Class I, minor importance, e.g., warehouses. Class 2, ordinary structures. Class 3, high importance, e.g., power plants. Summary table, Seismic Design Workflow Step ASCE 7 Eurocode 8 is 1893 Determine hazard MCER ground motions PGA and soil specific spectra zone factor, backslash, Z backslash, calculate base shear backslash, V equals C underscore S backslash dot W backslash, F underscore B equals S underscore D, T, backslash dot M backslash lambda backslash, V equals, zig slash R, backslash dot W backslash, apply importance backslash, I underscore E equals 1.0 backslash, importance class. Multiplier occupancy factor discussion questions. 1. Why does a hospital require higher importance factors than a warehouse? 2. How do soil conditions influence the choice between ELF and response spectrum analysis? 3. Should global codes harmonize seismic design approaches, or respect regional variability? Conclusion: this chapter equips engineers to navigate seismic codes, balance load combinations, and prioritize critical infrastructure. By aligning with ASCE 7, Eurocode 8, or IS 1893, professionals ensure structures meet safety, functionality, and resilience goals in earthquake-prone regions. Chapter 5, Reinforced Concrete Structures. This chapter explores the design principles and real-world applications of reinforced concrete, RC, structures in seismic regions, emphasizing ductile detailing, lateral load-resisting systems, and lessons from Chile's 2010 earthquake. 5.1 Ductile detailing, beam column joints, confinement, and lap splices. Key concepts: ductility, enables structures to undergo large deformations without catastrophic failure, absorbing seismic energy. Beam column joints, design, use closely spaced hoops to resist shear forces, ACI 318-19, minimum 4 ties in joint core. Avoid rebar congestion by staggering lap splices outside critical zones. Failure modes: shear failure, brittle, versus flexural yielding, ductile. Confinement, spiral or hoop reinforcement in columns, e.g., ACI 318's special moment frames requirements. Enhances concrete's compressive strain capacity, delaying crushing. Lap splices, located in regions of low stress, mid-span for beams, mid-height for columns. Length determined by rebar size, concrete strength, and seismic demand, e.g., Class B splices for moderate seismic zones. Example: in the 1994 Northridge earthquake, poorly confined columns failed due to concrete spalling, underscoring the need for stringent detailing. 5.2 Shear walls and moment-resisting frames. Shear walls, function, resist lateral loads via in-plane stiffness, common in high-rise buildings. Design considerations, boundary elements, heavily reinforced edges to prevent buckling under compression, ACI 318, epsilon underscore C GIC 0.003 Coupling beams, link adjacent shear walls, requiring diagonal reinforcement for ductility. Moment resisting frames, function, resist lateral loads through rigid beam column connections. Design considerations, strong column weak beam, ensure columns remain elastic while beams yield, FEMA 356. Panel zones, reinforce joint regions to withstand shear from beam moments. Comparison, feature shear walls moment frames stiffness high moderate construction cost higher, material intensive, lower, simpler formwork, best for high seismic zones, tall buildings low to mid-rise, open floor plans 5.3 Case study, Chile's 2010 earthquake and post-tensioned buildings event overview, magnitude, 8.8 MW, one of the strongest recorded earthquakes. Impact, 525 fatalities, but only 0.1% of high-rise buildings collapsed due to robust seismic codes. Post-tensioned, PT, systems, design, and bonded tendons allow self-centering, reducing residual displacements. Hybrid systems, combine PT frames with energy-dissipating devices, e.g., dampers. Performance, Torre titanium, Santiago PT concrete core survived with minor cracks. Costanera Center, Latin America's tallest building used PT slabs to limit deflection. Lessons learned, code enforcement, Chile's NCH 433 code mandates strict ductile detailing and PT compatibility checks. Quality control, post-tensioning requires rigorous inspection of tendon grouting and anchorage. Challenges, corrosion risk, and bonded tendons need corrosion-resistant sheathing. Complexity, skilled labor and advanced formwork required. Key takeaways 1. Ductile detailing, prevents brittle failure by ensuring plasticity in controlled regions. 2. System selection, shear walls for stiffness, moment frames for flexibility, and PT systems for resilience. 3. Chile's model, integration of stringent codes, hybrid systems, and post-tensioning offers a blueprint for seismic resilience. Discussion questions 1. How does confinement reinforcement enhance the ductility of RC columns? 2. Why might a designer choose PT systems over conventional RC in seismic zones? 3. What lessons from Chile's 2010 earthquake can apply to regions with lax building codes? Conclusion: reinforced concrete structures, when designed with ductile detailing and innovative systems like post-tensioning, can achieve remarkable seismic performance. Chile's 2010 earthquake exemplifies how engineering rigor and code compliance save lives, offering global lessons in resilience. Chapter 6, Steel structures. Steel structures are pivotal in seismic design due to their strength, ductility, and adaptability. This chapter explores advanced seismic-resistant steel systems, connection strategies, and real-world applications, drawing lessons from Japan's 2011 Tohoku earthquake. 6.1 Concentrically and eccentrically braced frames. Concentrically braced frames, CBFs, design, braces intersect at joints, forming vertical trusses to resist lateral forces. Types: X bracing, chevron, V bracing, and single diagonal systems. Advantages: high stiffness and strength, ideal for wind and moderate seismic zones. Cost-effective for low to mid-rise buildings. Limitations: limited ductility due to brace buckling under severe shaking. Post-buckling behavior can lead to sudden strength loss. Eccentrically braced frames, EBFs, design, braces connect to beams eccentrically, creating a sacrificial link beam that yields to dissipate energy. Link behavior, acts as a fuse, protecting primary members from damage. Advantages: enhanced ductility and energy dissipation, 2-3x more than CBFs. Balances stiffness and redundancy for high seismic zones. Code compliance, ASCE 341 mandates link rotation capacity, e.g., 0.08 rad for short links. Comparison, feature CBFs ductility low moderate high construction cost lower higher, complex connections, best for moderate seismic regions high seismic regions 6.2 moment resisting connections and reduced beam sections moment resisting frames, MRFs, design, rigid beam column connections resist lateral forces via flexural strength. Welded unreinforced flange bolted web, WUFB common pre-Northridge design. Post-Northridge modifications, avoid brittle fractures using improved weld details. Reduced beam sections, RBS, concept, strategically undercut beam flanges near connections to shift plastic hinges away from columns. Benefits, prevents connection failure by promoting ductile yielding in beams. Complies with ASCE 358's strong column weak beam principle. Design parameters, cut geometry, radius or straight taper, e.g., 50% flange reduction over 1/3 beam span. Case study, 1994 Northridge earthquake, WUFB connections failed due to weld fractures, RBS became standard in U.S. codes. 6.3 Case study, Japan steel skyscrapers and the 2011 Tohoku earthquake event overview, 2011 Tohoku earthquake, MW 9.0, the strongest in Japan's recorded history. Impact on steel structures, Tokyo Skytree, 634 m minimal damage due to hybrid steel frame and central concrete shaft. Yokohama Landmark Tower, 296 m utilized EBFs and viscous dampers, zero structural damage. Key design innovations, hybrid damping systems, combined base isolation, rubber bearings, with tuned mass dampers. High-strength steel, SN490 SN690 enhanced yield strength, 355-690 MPa, and toughness. Buckling restrained braces, BRBs dissipated energy without buckling, used in Sendai's high-rises. Post-earthquake reforms, revised building standard law, enforced stricter drift limits, 1/200 rad, and mandatory damping in skyscrapers 60 m. Advanced simulation, AI-driven seismic modeling for high-rise designs. Key takeaways 1. EBFs versus CBFs. EBFs offer superior energy dissipation for high-risk zones, while CBFs suit moderate regions. 2. RBS connections, critical for ductile MRFs, preventing brittle failures observed in pre-Northridge designs. 3. Japan's leadership, hybrid systems, BRBs, and stringent codes set a global benchmark for steel skyscraper resilience. Discussion questions 1. How does the strong column weak beam principle enhance seismic performance in steel MRFs? 2. Can EBFs replace MRFs in high-rise buildings, or are hybrid systems preferable? 3. What lessons from Japan's steel design practices can apply to skyscrapers in the Ring of Fire? Conclusion: steel structures, when designed with advanced bracing, ductile connections, and hybrid damping, exemplify seismic resilience. Japan's success during the 2011 Tohoku earthquake underscores the value of innovation, rigorous codes, and continuous learning in earthquake engineering. Chapter 7, Masonry and Timber Structures. This chapter explores seismic resilience strategies for masonry and timber structures, balancing traditional techniques with modern innovations. Below is a structured overview. 7.1 Reinforced masonry, horizontal and vertical reinforcement principles. Horizontal reinforcement, purpose, resists shear forces and distributes lateral loads. Implementation, steel bars or ladder-type reinforcement embedded in mortar joints, e.g., bed joint reinforcement. Vertical reinforcement, purpose, enhances flexural strength and ductility. Implementation, rebar placed in grouted cavities of masonry units, e.g., concrete blocks. Design considerations, grouting, ensures bond between rebar and masonry, critical for load transfer. Code compliance, ASCE 5-22 and TMS 402-23 specify spacing, cover, and minimum reinforcement ratios. Case study, 2011 Christchurch earthquake, reinforced masonry buildings showed significantly less damage compared to unreinforced ones. 7.2 Cross-laminated timber, CLT, and resilient joint CLT characteristics, engineered strength. Cross-laminated layers provide bidirection load capacity and dimensional stability. Seismic advantages, lightweight nature reduces inertial forces, inherent flexibility allows energy dissipation. Resilient joint systems, connectors, self-centering steel brackets or friction dampers, e.g., X-lam connectors, accommodate movement. Design strategies, slotted bolts, allow controlled sliding during shaking. Hybrid systems, combine CLT with steel or concrete cores for enhanced stiffness. Case study, Salvador School, Chile, CLT structure with resilient joints survived the 2010 earthquake with minimal damage. 7.3 Retrofitting historic masonry buildings challenges, material compatibility, original lime mortar and soft bricks require non-invasive techniques. Aesthetic preservation, retrofits must maintain historical integrity. Techniques, internal reinforcement, FRP wrapping, carbon/glass fiber sheets applied to walls/columns for tensile strength. Grout injection, stabilizes cracked masonry without altering. External systems, base isolation, install isolators beneath foundations to decouple building from ground motion, e.g., Rome's Colosseum. Tie rods/buttresses, discreetly added to prevent wall bulging. Case study, Istanbul's Hagia Sophia, FRP strengthened domes and arches to meet modern seismic standards. Comparative analysis aspect reinforced masonry CLT structures historic retrofits material behavior FRP brittle ductile with rebar flexible, lightweight brittle stabilized with construction cost moderate, labor intensive, high, prefabrication, very high, specialized labor, seismic performance good with proper detailing. Retrofit, excellent, energy dissipation, variable, depends on sustainability materials high embodied carbon, cement, low carbon, renewable timber, preserves existing key takeaways 1. Reinforced masonry, transforms brittle walls into ductile systems through strategic rebar placement. 2. CLT, leverages engineered timber and resilient joints for lightweight, high-performance seismic design. 3. Historic retrofits, balances preservation with safety using FRP, base isolation, and grout injection. Discussion questions 1. How does CLT's anisotropy influence its use in multidirectional seismic zones? 2. Can base isolation be feasibly applied to small-scale historic buildings? 3. What cost-benefit trade-offs exist between CLT and reinforced masonry in urban seismic zones? Conclusion: masonry and timber structures, when thoughtfully designed or retrofitted, offer viable paths to seismic resilience. By integrating traditional materials with modern engineering, professionals can safeguard both heritage and new construction in earthquake-prone regions. Chapter 8, Base Isolation and Energy Dissipation Devices. This chapter explores advanced seismic protection systems that decouple structures from ground motion and dissipate seismic energy, combining theory, design principles, and real-world applications. 8.1 Elastomeric and lead rubber bearings. Elastomeric bearings, design, laminated rubber steel, alternating layers of natural rubber and steel plates for vertical stiffness and horizontal flexibility. Low damping rubber, LDR, natural rubber with 5-10% damping. Applications, bridges, e.g., San Francisco-Oakland Bay Bridge. Low to moderate seismic zones. Lead rubber bearings, LRBs, design, lead core, yields under shear to dissipate energy, 15-20% damping. High damping rubber, HDR, enhanced energy absorption. Applications, critical facilities, hospitals, data centers, in high-risk zones. Christchurch Women's Hospital, ASCE survived 2011 earthquake unscathed. Key parameters: effective stiffness, /K_text EFF equals /frac F_text max, F_text min /delta_text max /delta_text min damping ratio, /beta equals /frac W_D4 /pi W_S where W_D equals energy dissipated per cycle. 8.2 Viscous dampers and tuned mass dampers. Viscous dampers, mechanism, fluid, silicone oil, forced through orifices converts kinetic energy to heat. Force velocity relation, F equals C dot V N where C equals damping coefficient, N equals 0.31.0 Applications, Tokyo Skytree, 400 dampers reduce wind/earthquake sway. LA City Hall retrofit, 54 dampers added for seismic resilience. Tuned mass dampers, TMDs, design, mass rod spring system, tuned to structure's natural frequency, F_text TMD equals F_text structure /. Pendulum TMDs, used in skyscrapers, e.g., Taipei 101, 660-ton steel ball. Limitations, effective for narrow frequency ranges, less suited for broadband seismic energy. Comparison, feature viscous dampers tuned mass dampers energy dissipation broadband, all frequencies, narrowband, specific frequency, space requirements compact, wall/brace integration, large, mass block/mechanical space, cost moderate, $20K $50K per damper, high, $1 million for skyscrapers, 8.3 Case study, San Francisco City Hall retrofit background, original. Structure, completed in 1915, unreinforced masonry with seismic vulnerabilities. Retrofit motivation, 1989 Loma Prieta earthquake caused $20 million and damage. Retrofit strategy, 1 base isolation, 530 lead rubber bearings installed under the foundation. Design parameters, load capacity, 1,500 tons per bearing. Displacement capacity, 24 inches, 610 millimeters. 2 supplemental damping, 134 viscous dampers added to limit displacement. 3 structural enhancements, steel frame reinforcement to protect historic dome. Performance, 1994 Northridge earthquake, minimal damage despite 6.7 MW shaking. Cost, $293 million, 1998, extending lifespan by 100 plus years. Lessons learned, heritage preservation, isolation minimizes invasive alterations. Hybrid systems, combining isolators and dampers optimizes cost/performance. Key takeaways 1. Base isolation, ideal for decoupling structures from ground motion but requires careful bearing design. 2 dampers, viscous dampers handle broadband energy, TMDs target specific frequencies. 3 Hybrid retrofit, San Francisco City Hall exemplifies how combining isolation and damping achieves resilience in historic structures. Discussion questions 1. Why are lead rubber bearings preferred over elastomeric bearings in high seismic zones? 2. Can TMDs be effective in low-rise buildings, or are they limited to skyscrapers? 3. How might climate change, e.g., temperature swings, affect viscous damper fluid performance? Conclusion: base isolation and energy dissipation devices revolutionize seismic protection, enabling structures to ride out earthquakes with minimal damage. The San Francisco City Hall retrofit serves as a global benchmark, proving that even century-old buildings can achieve state-of-the-art resilience. Chapter 9, Seismic Retrofitting Techniques. This chapter explores advanced methods to enhance the seismic resilience of existing structures, focusing on practical applications and lessons from historical earthquakes. 9.1 FRP, Fiber-Reinforced Polymer, Wrapping Overview, FRP composites, carbon, glass, or aramid fibers embedded in epoxy resin, are externally bonded to structural elements to improve strength and ductility. Key applications: column confinement, prevents shear failure and concrete spalling by providing lateral restraint. Beam strengthening, increases flexural capacity and delays cracking. Masonry walls, enhances tensile strength in unreinforced masonry. Process: 1. Surface preparation, clean and grind substrate to ensure adhesion. 2. Application, wrap FRP sheets around columns/beams or laminate onto walls. 3. Curing, allow resin to harden under controlled conditions. Advantages: lightweight, corrosion resistant, and minimally invasive. High strength to weight ratio, e.g., carbon FRP has 10x the tensile strength of steel. Case study: 2016 Italy earthquake, FRP strengthened schools in Amatrai survived MW 6.2 shaking with minor damage. Limitations: sensitive to fire and UV exposure, requires protective coatings. Dependent on skilled labor for installation. 9.2 Jacketing and supplemental damping jacketing techniques, steel jackets, wrapped around columns to enhance shear/flexural capacity. Example, Los Angeles Veterans Affairs Hospital retrofit post Northridge. Concrete jackets, increase cross-sectional area and confinement, ideal for bridge piers. Supplemental damping, viscous dampers, dissipate energy via fluid motion, e.g., San Francisco's Transamerica Pyramid. Friction dampers, sliding plates convert kinetic energy to heat, e.g., Istanbul's historic mosques. Design considerations: hybrid systems, combine jacketing with dampers for multi-hazard resilience. Code compliance, ASCE 41 guidelines for retrofit force calculations. 9.3 Retrofitting soft-story buildings, lessons from the 1994 Northridge earthquake. Soft-story vulnerability, weak first stories, e.g., open parking, retail spaces, collapse due to inadequate lateral resistance. Northridge impact, 50+ soft-story buildings collapsed, prompting code reforms, e.g., LA Ordinance 183,893. Retrofitting strategies: 1. Shear walls, add plywood or steel panels to first-story openings. 2. Steel braces, diagonal bracing in open bays, e.g., moment frames. 3. Concrete cores, stiffen central stairwell/elevator shafts. Case study: Los Angeles soft-story program, over 13,000 buildings retrofitted since 2015, reducing collapse risk by 70%. Cost and challenges: average retrofit cost, $60,000, $150,000 per building. Tenant relocation and permit delays are common hurdles. Comparative analysis technique best for cost performance gain FRP wrapping localized strengthening $50 200/square foot 30-50% strength increase steel jacketing column retrofits $100 300/column 2 3x ductility improvement shear wall soft story buildings $20 50/square foot 50-70% risk reduction. Key takeaways: 1. FRP, ideal for rapid, non-invasive upgrades but requires environmental protection. 2. Jacketing/damping, balances strength and energy dissipation for critical infrastructure. 3. Soft-story retrofits, code-driven programs, e.g., LA, SF, save lives by addressing systemic vulnerabilities. Discussion questions. 1. How do FRP and steel jacketing compare in terms of life cycle costs? 2. Can supplemental damping replace traditional retrofitting in historic buildings? 3. What policy tools best incentivize soft-story retrofits in private buildings? Conclusion: the 1994 Northridge earthquake reshaped seismic retrofitting practices, proving that proactive upgrades save lives and reduce economic losses. By integrating FRP, jacketing, and soft story solutions, engineers can transform vulnerable structures into resilient assets, bridging the gap between historic preservation and modern safety standards. 10 Emerging Technologies in Earthquake Engineering. 10.1 Self-centering structures with shape memory alloys, SMAs. Definition and application. SMAs are advanced materials that remember their original shape, reverting after deformation. In earthquake engineering, they are integrated into structural elements like beam column joints, braces, or reinforcement bars to enable buildings to recenter post-seismic activity. Benefits: reduces residual deformations, minimizing repair costs and downtime. Enhances resilience in frequent seismic events. Challenges: high material costs compared to traditional steel. Long-term durability under cyclic loading needs further research. Examples: research at institutions like Stanford University and projects in Japan post-Tohoku earthquake explore SMA-based dampers and rebar. 10.2 3D printed earthquake-resistant components. Definition and application. Additive manufacturing creates complex geometries, e.g., lattice structures, topology-optimized components, that enhance energy dissipation. Materials like fiber-reinforced polymers or high-performance concrete are used. Benefits: custom designs improve seismic performance, e.g., shock-absorbing shapes. Reduces material waste and enables rapid prototyping. Challenges: scalability for large structural elements remains limited. Material strength and ductility must match conventional methods. Examples: Zurich's 3D printed concrete columns and NASA's research on lightweight seismic resistant habitats. 10.3 AI-driven seismic risk prediction and monitoring. Definition and application. AI algorithms analyze data, historical seismic activity, real-time sensor inputs, geological surveys, to assess risks and monitor structural health. Benefits: improves early warning systems and risk assessment accuracy. Enables real-time decision-making, e.g., shutting utilities during shaking. Challenges: earthquake prediction remains probabilistic, not exact. Requires high-quality data and interdisciplinary collaboration. Examples: California's Shake Alert system and AI models in Japan predicting aftershock patterns. Integration and future outlook. SMAs may become cost-effective with material advancements, paired with traditional systems. 3D printing could standardize bespoke, eco-friendly components as technology scales. AI will likely merge with IoT for smarter infrastructure management, enhancing sustainability through optimized designs. Sustainability and challenges. SMAs and 3D printing reduce life cycle environmental impacts via durability and waste reduction. Regulatory and training gaps must be addressed to adopt these technologies widely. By balancing innovation with practical considerations, these technologies promise to transform earthquake resilience, offering safer, adaptive, and sustainable infrastructure. Part 4, Case Studies and Global Practices. 11. High-risk regions, Design Innovations. 11.1 Japan's tsunami-resistant coastal infrastructure. Definition and application. Following the catastrophic 2011 Tohoku earthquake and tsunami, Japan pioneered multilayered coastal defenses combining engineering, urban planning, and community preparedness. Key innovations include massive seawalls and breakwaters, e.g., the Kamaishi breakwater, world's deepest, and reinforced concrete barriers along Fukushima's coast. Vertical evacuation towers, earthquake-resistant structures, e.g., in Sendai and Rikuzen Takeda, where residents can flee to higher floors during tsunamis. Smart floodgates, automated gates triggered by seismic sensors to block tsunami waves from entering rivers. Benefits: drastically reduced casualties in subsequent tsunamis, e.g., 2016 Fukushima earthquake. Integration with early warning systems enhances evacuation efficiency. Challenges: environmental impact on coastal ecosystems and fisheries. high maintenance costs and public debate over concrete dependency. Examples: reconstruction of Tohoku's coastline with disaster-resilient cities. The Onagawa town reconstruction, featuring elevated infrastructure and tsunami-resistant zoning. 11.2 New Zealand's seismic isolation in Christchurch rebuild definition and application. After the 2011 Christchurch earthquakes, New Zealand prioritized base isolation and low-damage design to protect heritage and modern buildings. Techniques include lead rubber bearings, LRBs installed in critical infrastructure like the Christchurch Art Gallery and Te Pei Convention Centre, sliding isolation systems, used in historic churches, e.g., Christchurch Cathedral, to preserve architecture while enhancing safety. Benefits: minimized structural damage during the 2016 Kaikoura earthquake. Enabled faster recovery of economic and cultural hubs. Challenges: high upfront costs for retrofitting heritage buildings. Balancing modern safety standards with historical preservation. Examples: the SIRT, Stronger Christchurch Infrastructure Rebuild Team, program, which rebuilt 80% of the city's horizontal infrastructure with seismic resilience. The Cardboard Cathedral, a temporary seismic-resistant structure built with recycled materials. 11.3 Turkey's failures and reforms post-2023 Kahramanmaraş earthquakes definition and application. The 2023 Kahramanmaraş earthquakes, MW 7.8 and 7.5, exposed systemic flaws in Turkey's construction practices, prompting urgent reforms, stricter building codes, mandatory use of high-quality steel, seismic isolators, and rigorous inspections. Retrofit campaigns, government-funded programs to reinforce 1.5 million at-risk buildings. Accountability measures, prosecution of contractors for violations and bans on amnesty laws that legalized unsafe structures. Benefits: improved public trust in infrastructure safety. Adoption of international standards, e.g., Eurocode 8, for seismic design. Challenges: legacy of corruption in construction sectors and rapid urbanization. Financial and logistical hurdles in retrofitting informal settlements. Examples: the Build Back Better initiative in Hatay and Gaziantep, emphasizing modular, earthquake-resistant housing. Istanbul's Metropolitan Municipality Earthquake Risk Management Department, established to audit 100,000 plus buildings annually. Integration and lessons learned. Japan, demonstrates the need for layered defenses, engineering and community preparedness. New Zealand, highlights how seismic isolation can protect both modern and historic assets. Turkey, a cautionary tale on the consequences of lax regulations and the urgency of systemic reform. Future outlook: global adoption. High-risk countries like Indonesia and Chile are integrating Japanese-style tsunami barriers and ANSI-inspired isolation techniques. Technology synergy, AI and IoT for real-time monitoring of coastal infrastructure, Japan, and building health, Turkey. Sustainability and equity, Japan seawalls versus ecological balance, green infrastructure, e.g., mangrove buffers, is being tested as a complement. Turkey's focus on affordable retrofits to protect low-income communities. By learning from these regional successes and failures, the global engineering community can advance toward safer, equitable, and culturally sensitive seismic resilience strategies. Part 4, Case Studies and Global Practices 12. Urban Resilience and Community Preparedness. 12.1 Earthquake Early Warning Systems, Mexico and California definition and application. Earthquake early warning, EEW, systems detect primary seismic waves, P waves, to provide seconds to minutes of advance alert before destructive secondary waves, S waves, arrive. Mexico, operates the Seismic system, established 1991, delivering alerts via radio, TV, sirens, and mobile apps. Notable during the 2017 Puebla earthquake, M7.1, offering 60 seconds warning in Mexico City. California, the Shake Alert System, rolled out in 2019, sends alerts via smartphones, public address systems, and automated infrastructure shutdowns, e.g., trains, utilities. Benefits: reduces casualties by enabling protective actions, e.g., drop, cover, hold on. Critical infrastructure can be safeguarded, e.g., hospitals, transportation networks. Challenges: Mexico, limited coverage in rural areas, reliance on outdated communication infrastructure. California, public awareness gaps and funding shortages for full sensor network deployment. Both, false alarms and latency issues during complex fault ruptures. Examples: Seismic's success in mitigating damage during the 2022 Michoacan earthquake, M7.7. Shake Alert integration with Bay Area Rapid Transit, BART, to halt trains automatically. Future outlook: expansion of sensor networks and AI-driven algorithms to improve accuracy. Cross-border collaboration for shared seismic risks, e.g., San Diego-Tijuana region. 12.2 Community training and building code enforcement in Nepal definition and application, post-2015 Gorkha earthquake, M7.8, Nepal prioritized grassroots training and stricter enforcement of seismic codes. Community training: the National Society for Earthquake Technology Nepal, NSET, trains masons in earthquake-resistant techniques, e.g., reinforced masonry, retrofitting. Building codes: revised 2020 National Building Code mandates reinforced concrete frames and inspections, even in rural areas. Benefits: over 50,000 masons trained since 2015, rebuilt schools and homes withstood 2023 Dodi earthquake, M5.7. Public awareness campaigns increased household preparedness, e.g., emergency kits, evacuation drills. Challenges: informal construction persists due to cost barriers and lack of enforcement in remote villages. Cultural resistance to abandoning traditional, non-engineered, building methods. Examples: NSET Safe Schools Program, retrofitted 1,000 plus schools with steel-braced frames. Bhaktapur Municipality, enforced heritage-compliant seismic upgrades in historic areas. Future outlook: scaling up mobile inspection units and subsidies for low-income households. Integrating indigenous knowledge with modern engineering practices. 12.3 Resilient infrastructure for informal settlements definition and application, targeting informal settlements, slums, with poor structural integrity. Initiatives focus on retrofitting, community-led planning, and hybrid formal-informal governance. Retrofitting: use of low-cost materials, e.g., bamboo, tire foundations, to reinforce existing structures. Community-led upgrading: organizations like Slum Dwellers International, SDI, facilitate participatory design of drainage, roads, and emergency shelters. Benefits: Nepal, community-managed water points and evacuation routes in Kathmandu slums reduced 2023 monsoon-related casualties. Ecuador, Quito's Barrio Seguro program combined microcredit loans with seismic retrofitting. Challenges: land tenure insecurity discourages investment in permanent upgrades. Limited government support and reliance on NGO funding. Examples: Haiti, post-2010 earthquake, build change trained locals to construct hurricane and earthquake-resistant homes. Philippines, Manila's People's Plans integrate informal settlers into citywide disaster risk reduction strategies. Future outlook: leveraging geospatial tech, e.g., drones, GIs, to map vulnerable settlements. Policy reforms to recognize informal dwellers as stakeholders in urban planning. Integration and lessons learned, early warning and community training. Mexico's Seismic alerts are paired with school drills, mirroring Nepal's NSET programs. Informal settlements and policy: California's Shake Alert must address mobile home parks, akin to Quito's slum upgrading efforts. Sustainability and equity: Mexico/California, ensure EEW access for marginalized groups, e.g., non-Spanish speakers, homeless populations. Nepal/informal settlements, prioritize gender-inclusive training and land rights for women-led households. Global relevance, EEW systems expanding in Indonesia and Chile. Nepal's model informs earthquake-prone Himalayan regions, e.g., India, Bhutan. Informal settlement strategies critical for global south cities facing rapid urbanization. By merging technology, policy, and community agency, these case studies underscore that urban resilience hinges on inclusivity and adaptive governance, ensuring no community is left behind in the race to mitigate seismic risk. Part B, Codes, Policies, and Future Directions. 13. Policy Frameworks for Seismic Safety. 13.1 National Earthquake Hazard Reduction Program, NERP, Definition and Application, established in 1977 following the San Fernando earthquake. NERP is a U.S. federal initiative coordinated by FEMA, USGS, NIST, and NSF. It focuses on research, advancing earthquake science and engineering practices. Public education, campaigns like Great Shakeout drills. Building codes, development of seismic standards, e.g., FEMA P50 guidelines. Benefits, reduced fatalities and economic losses through improved infrastructure resilience. Tools like ASCE for risk assessment and community planning. Challenges, funding instability and interagency coordination hurdles. Balancing rapid urbanization with retrofitting older structures. Examples, adoption of updated building codes in high-risk states, e.g., California, Alaska. Post-1994 Northridge earthquake reforms in construction practices. Future outlook, expanding NERP scope to address climate change-induced seismic risks, e.g., liquefaction. Leveraging AI for real-time risk modeling and public alerts. 13.2 Incentivizing retrofitting, tax breaks and grants. Definition and application, financial mechanisms to encourage seismic upgrades in vulnerable buildings. Grants, California's Earthquake Brace and Bold program offers up to $3,000 for home retrofits. Tax credits, federal tax deductions for retrofitting commercial properties. Benefits, increased retrofit rates in high-risk zones, e.g., 20,000 plus homes upgraded in California since 2014. Protection of historic buildings while enhancing safety, e.g., San Francisco's Victorians. Challenges, limited accessibility for low-income households. Ensuring compliance with engineering standards. Examples, Japan's subsidy programs for retrofitting pre-1981 buildings. Turkey's post-2023 earthquake grants for residential seismic upgrades. Future outlook, innovative financing, green bonds for retrofitting public infrastructure. Equity focus, sliding scale incentives based on income and risk level. 13.3 Global collaboration, UN Sendai Framework definition and application, adopted in 2015, the Sendai Framework is a 15-year UN plan to reduce disaster risks, emphasizing preparedness, early warning systems and community training. Resilient infrastructure, enforcing seismic codes in vulnerable regions. Benefits, alignment of national policies, e.g., Nepal's 2020 Building Code, with global standards. Shared best practices, such as Chile's tsunami-resistant urban planning. Challenges, disparities in funding and technical capacity between nations. Political inertia in prioritizing long-term resilience over short-term costs. Examples, Indonesia's adoption of Japan-style tsunami barriers post-Sendai. The Global Earthquake Model, GEM, fostering international data sharing. Future outlook, integrating AI and IoT into Sendai's monitoring frameworks. Strengthening partnerships for cross-border seismic risk management, e.g., Himalayan regions. Integration and future directions, NERP and Sendai synergy. U.S. expertise in risk modeling could aid global South nations via Sendai partnerships. Tech-driven policies, use 3D printing and AI, as in Part 4, to lower retrofitting costs and improve compliance. Sustainability and equity, NERP, prioritize retrofitting in marginalized communities, e.g., mobile home parks. Sendai, advocate for land rights in informal settlements to enable safer construction. Global relevance, tax incentives, replicate California's model in earthquake-prone regions like Iran and Italy. Sendai compliance, metrics to track reductions in seismic mortality and economic loss by 2030. By harmonizing national programs like NERP, financial incentives, and global frameworks like Sendai, policymakers can forge a path towards seismic resilience that is both technologically advanced and socially equitable. The future lies in adaptive governance, cross-sector collaboration, and empowering communities to build safer tomorrows. Part V, Codes, Policies, and Future Directions 14. Future Challenges and Innovations 14.1 Climate Change and Induced Seismicity Definition and Application. Induced seismicity refers to earthquakes triggered by human activities, increasingly linked to climate change mitigation efforts. Examples include geothermal energy extraction, fluid injection for geothermal power, e.g., projects in Iceland and California, causing minor tremors. Glacial rebound, melting ice sheets, e.g., in Alaska and Greenland, reducing crustal pressure, potentially reactivating faults. Carbon capture and storage, CCS underground CO injection altering subsurface stress fields. Benefits, mitigating climate change via renewable energy and CCS, despite seismic risks. Improved monitoring technologies to balance energy needs and safety. Challenges, complex interactions between climate policies and geological systems. Regulatory gaps in managing induced seismicity from green technologies. Examples, Oklahoma's fracking-induced earthquakes, 2009-2016, prompting stricter wastewater injection regulations. Basel, Switzerland's geothermal project halted in 2006 due to magnitude 3.4 quakes. Future outlook, AI-enhanced predictive models to assess seismic risks of climate interventions. International guidelines for safe geothermal and CCS operations. 14.2 Bio-inspired design, mimicking nature for resilience definition and application, leveraging biological systems to enhance seismic resilience, flexible structures, bamboo-inspired buildings, e.g., Vietnam's VOTR and Jimha architects, that bend without breaking. Self-healing materials, concrete with bacteria, as in bones, to repair cracks autonomously. Redundant networks, root-like foundation systems distributing stress, akin to tree root networks. Benefits, sustainable, energy-efficient solutions with inherent adaptability. Potential cost savings over traditional retrofitting. Challenges, scaling lab innovations to real-world applications. Interdisciplinary collaboration between biologists and engineers. Examples, Caltech's seismic spider concept, mimicking spiderweb elasticity. Japan's Shinkansen train pantographs modeled after kingfisher beaks for stability. Future outlook, integration with 3D printing for customizable bio-inspired components. Policy incentives for nature-based design in building codes. 14.3 Quantum computing for seismic simulations definition and application. Quantum computing uses qubits to solve complex problems exponentially faster than classical computers. Applications include, fault modeling, simulating tectonic interactions at unprecedented resolution. Risk assessment, optimizing evacuation routes and infrastructure reinforcement. Benefits, real-time earthquake forecasting with high accuracy. Efficient resource allocation for disaster preparedness. Challenges, current quantum hardware limitations, e.g., error rates, qubit stability. Developing domain-specific algorithms for geophysical problems. Examples, IBM's collaboration with universities to model seismic wave propagation. QUBIT for QUAKE research initiative exploring quantum-enhanced simulations. Future outlook, hybrid quantum classical models bridging current tech gaps. Democratizing access via cloud-based quantum platforms for global risk management. Integration and future directions, synergies, bio-inspired designs could use quantum simulations to optimize natural analogs, while addressing climate-induced seismic risks. Equity, ensuring low-income regions benefit from quantum advancements and bio-inspired affordability. Sustainability and challenges, biodesign, reduces material waste but requires life cycle analysis. Quantum tech, energy-intensive hardware versus long-term resilience gains. Global relevance, induced seismicity, critical for regions adopting geothermal/CCS, e.g., Kenya, Norway. Bio-inspired solutions, ideal for disaster-prone global south with limited resources. Quantum computing, collaborative frameworks like the UN Sendai framework could fund shared quantum resources. By confronting climate-linked seismic risks, harnessing nature's genius, and unlocking quantum potential, the future of earthquake resilience lies in adaptive, equitable, and cross-disciplinary innovation. Policymakers must foster ecosystems where science, sustainability, and social justice converge to safeguard vulnerable communities. Appendices A seismic design formulas and conversion tables. Key formulas: 1 base shear calculation, ASCE 7-22 V equals C_S_W_C_seismic seismic response coefficient, W effective seismic weight 2. Natural period estimation, Eurocode 8 /T_A equals C_T /H3/4 /C_T building type coefficient, H building height 3. Ductility demand, FEMA P58 /mu equals /frac /delta_text max /delta_y /delta_text max maximum displacement /delta_y yield displacement. Conversion tables, acceleration, 1 text g equals 9.81 text m/s2 force 1 text kn equals 0.2248 text kip length 1 text m equals 3.281 text foot -b sample retrofitting plans and details. 1. Concrete shear wall addition, scope, strengthen soft story buildings. Materials, grade 60 rebar, 30 MPa concrete. Details, anchorage to foundation, lap splices per ACI 318. 2 steel braced frame retrofit, scope, reduce lateral drift in mid-rise buildings. Details, concentric/eccentric bracing, HSS sections. 3 base isolation for historic structures, scope, install lead rubber bearings under foundations. Specifications, refer to FEMA 547 for isolator spacing. Sample diagram, sketch, cross-section of retrofitted beam column joint with fiber reinforced polymer, FRP, wraps. C compliance checklists for ASCE 41 and FEMA P58. ASCE 41-17 checklist. 1 Performance objective, define immediate occupancy, IO, or life safety, LS. 2 Evaluation, conduct linear/nonlinear analysis for existing structures. 3 Retrofit design, verify component capacities using Tier 3 guidelines. FEMA P58 checklist. 1 Inventory, catalog building components and fragility curves. 2 Analysis, run Monte Carlo simulations for probabilistic loss estimation. 3 Reporting, document repair costs and downtime scenarios. D Glossary of seismic engineering terminology, ductility, ability of a material/structure to deform without breaking. Liquefaction, soil losing strength during shaking, behaving like liquid. Base isolation, decoupling structure from ground motion using bearings. Response spectrum, graph of max structural response versus natural period. P-delta effect, secondary moments due to lateral displacement and gravity loads. References peer-reviewed journals, 1 Earthquake Engineering and Structural Dynamics, Wiley. 2 Journal of Structural Engineering, ASCE. Industry Standards, 1 ASCE 7-22, Minimum Design Loads and Associated Criteria for Buildings and Other Structures. 2 FEMA P58, Seismic Performance Assessment of Buildings. 3 Eurocode 8, Design of Structures for Earthquake Resistance. Textbooks, 1 Mowell, J. 2015. Seismic Design of Reinforced Concrete Buildings. McGraw-Hill. 2 Chopra, A. 2017. Dynamics of Structures, Theory and Applications to Earthquake Engineering. Pearson. 3 Fardis, M. 2009. Seismic Design, Assessment, and Retrofitting of Concrete Buildings. Springer. Note, for full compliance, consult the latest editions of standards and region-specific codes, e.g., NZS 1170.5 for New Zealand, IS 1893 for India.